Okay, so Santosh, there is a vertical wind panel here showing participants. Is that visible on the shared screen, or you just see my slides or something else on the screen as well? Okay, only slides, right? That and there is nothing else on that, right? Because there's some Zoom sidebar and all वो सब नहीं है. Okay, okay, great, great. So welcome back. So let us start. So where were we when we left? We in the last lecture we understood that how crucial neutral hydrogen is to galaxies in the broader context of star formation, and then also we reviewed how hydrogen being the simplest atom, we can look at its hyperfine transition 21 centimeter line, and that provides us a very powerful tool to map the distribution of galaxy uh, H1 in our own galaxy to start with, and then how a combination of emission and absorption allowed us to understand that gas in our galaxy is actually distributed in two phases, one being cold neutral medium, another being warm neutral medium, right? So what we are seeing here on this image is the H1 map of our own galaxy, Milky Way. So you can see that most of the high column density H1 is actually confined to the disk of the galaxy. But in addition, there are also like extraplanar features, and we'll talk about some of them in a general context in a short while. So, but to conclude, when detailed observations of 21 centimeter line observations for our galaxy, what they have revealed that not only that we have two phases of SEM, one being cold neutral medium and another being warm neutral medium. When people try to simulate using understanding of various physical processes, because when we talk about a gas at a certain temperature, that a temperature is actually a result of a balance between various heating and cooling processes that are taking place in the ISM, right? For example, like if there is a radiation field that will lead to photoionization, and that electron that comes out with excess energy would actually be contributing to the heating up of the gas, right? So that's an example of heating. And cooling, on the other hand, for example, there is an atom which gets excited through collision to a higher energy level, and but it de-excites radiatively, and that photon escapes the cloud. So this will be an example of the loss of energy for the cloud. So there are a list of processes depending on the phase of the ISM, its metallicity, and its ambient environment that will contribute to heating. And similarly, on the other side, there will be a set of processes that will correspond to cooling. So if we can come up with this simple situation that the two phases in the ISM exist in kind of a pressure equilibrium, and we do this heating, balance the heating and cooling, then one can come up with a model like this, in which one finds that there is a range of pressures here. X-axis is a pressure plotted here, T is the temperature. There is a range of pressures where warm neutral medium exists in a stable phase. There is another set of uh, uh, pressure where the cold neutral medium is stable. But then there exists a range which is represented here by the dashed line, where the two phases are actually unstable, which means that like if there is a gas here, if I push it upwards, then it will move towards warm neutral medium and vice versa. So what has been observationally found that there exists actually at least 50% of the warm neutral medium, which is at least in actually in the unstable phase. So this is still like to understand how actually different phases of ISM are distributed just for the atomic phase, and how much of it is in warm neutral medium, how much in cold neutral medium, and what physical processes contribute to this balance and distribution is a field of active research. People are still trying to obtain more sensitive, better data to understand it further, and more simulations also are on way. So this is just a quick summary of what we discussed so far in terms of the distribution of CNM and warm neutral medium in our galaxy. So now let us shift our focus to the galaxies in general. So on left hand side, there is a cartoon where you can see that there is a disk of galaxy here, right? So and now we know that there will be an optical disk at the center, which is where the stars are actively being found. But then there will be an H1 disk which will extend further beyond that. and then this gas, the galaxies also acquire gas through accretion from the circumgalactic medium, because otherwise it cannot sustain that ongoing star formation in the galaxy. So this supply has to be maintained, otherwise at some point star formation will stop. And once the stars are formed, they will actually put a lot of radiative and mechanical feedback into the gas, and that can then lead to expulsion of gas through in the direction perpendicular to the disk, because that's where the least resistance is. And then this gas will go out. Some of it, depending on at what velocity it is ejected, it can go away, or it can actually fall back in the kind of a fountain. And it is this process and its interaction with the ambient environment which will lead to actually whether a galaxy in this Hubble classification, where would it eventually fall. Right. So observationally, what we are seeing here is a very basic plot for galaxies in general. On x-axis, what we have plotted here is the stellar mass, and y-axis is plotted the star formation rate. And this dashed blue dashed line, what you are seeing here, is called the main sequence of our star-forming galaxies. So you can see that there is a lot of galaxies falling along the main sequence, but then there are a lot of galaxies which are actually deviate away from the main sequence as well. And those are the galaxies which are actually either on the way of being quenched or have been quenched. Quenched means that like they don't have enough gas now to sustain star formation, so star formation has stopped. Right. So all the bulge dominated or red galaxies that we are seeing here on the left hand side of this plot here would be lying here in this region of this uh, this plot here. Right. So, what are the broader, some fundamental relations observationally that we know about the galaxy? So, if you go back to this plot here, what we were looking at, it, there are these galaxies, and it acquires gas from the circumgalactic medium. So, initially, if we even go back further, then we are talking about like the dark matter, right? And there are these instabilities which will grow in time with and whatever the baryonic matter is there will collapse under the gravity, and this is how eventually within the halos galaxies would form, right, and the disk would form. So these disks in principle would actually should carry the imprint of the dark matter halo in which they have been formed. So one of the very nice and fundamental relation that is used to investigate this kind of relation between a galaxy and its uh, dark matter halo is called the Tully-Fisher relation, right? What do we plot here on y-axis is plotted the magnitude, which you can see as like as proxy of the luminosity, and on the x-axis is the rotational velocity, right? So this is how you can see that like the different galaxies were formed. This is like the very first plot which was made in 1977, and over the years there have been various that have been made to this. Of course, like you can argue very easily that why should we plot luminosity here, because then the galaxies of different types wouldn't actually satisfy this relation, because like as we know that looking at this plot itself, the luminosity is not a very good indicator to capture galaxy population in general. So what should we use instead? So on y-axis one can replace this with something called stellar mass, and then you can find that like the relation gets tighter. But then there are also these low mass galaxies here, which are dwarf galaxies, which do not satisfy this relation. So another improvement was made to this actually, and that is to replace stellar mass now with the total baryonic mass or the dynamical mass in this case, and that then provides a much tighter relation with respect to this. And on x-axis we have the rotational velocity, and as you can imagine, since h1 is an excellent tracer of not only because of the fact that the h1 disk extends much farther than the optical disk, also that it's a spectral line. It is a very nice tracer to actually determine the kinematics or the rotational velocities of the galaxies, and that's some so it plays a very important role in this one very fundamental study. And currently a lot of deep observations are ongoing to build samples to investigate this as a function of redshift, like how it. So because these plots are made for the local galaxies, right? So what happens as we go at different redshift, then how the galaxies, whether their properties have been different or not, that's an active area of research. Another very nice relation that comes between H1 size and mass is the size of H1 disk of a galaxy and the total H1 mass that it contains. So what we are seeing here is that on y-axis we have an H1 diameter, H1 disk diameter, and on x-axis we have the total H1 mass of galaxy, both determined through H1 21 centimeter line observations. And what we are seeing here is that that this relation there's such a tight correlation exists, and for a wide variety of galaxies, right? So this scatter here which you are seeing, it actually does not depend on what is the mass of galaxy, what is the color of galaxy, or whether it is an H1 rich or towards the H1 poor galaxies. This relation continues to hold uh, really so well. This is one of the fundamental relations that have come out of H1 21 centimeter line observations for galaxy, and it will be very interesting to know that how it actually tests or stands to test as a function of redshift or as a function of even the environment. So to show you one example, this is an observation we carried out as part of our Meerkat absorption line survey. This is with the Meerkat telescope. So what you are seeing here in background is the optical image. So you can see the optical disks of different galaxy, and then in contours which are plotted are the H1 21 centimeter signal from the galaxies, right? So you can straight away one thing you can conclude that these are not isolated galaxies. This is a group of galaxies, right? So in the first lecture, we were discussing what are the kind of things that can happen to. So when galaxies interact with each other, then the tidal effects can actually lead to a situation where the H1 from a galaxy is expelled. For example, something like this can happen. But what we are seeing in this case is that the galaxy's H1 gas has been expelled not possibly because of the tidal interaction, but it is likely because of the fact that this gas galaxy is moving at a very high velocity and the intergroup medium is causing what is called the ramp pressure stripping, and as a result of that, the H1 from this galaxy has been stripped. Right. So these are the type of processes through which actually H1 from the galaxy can be affected. H1 content of a galaxy can be affected. Right. So what we did was it was interesting to see test whether if such a situation arises, then would galaxies still obey the DH1 MH1 mass relation. So instead of so in addition to what we did, we estimated what will be the sizes of the H1 disks of these galaxies on the basis of their optical diameter. And earlier in the first lecture, we understood that there exists a very nice correlation between H1 size and optical sizes of the galaxies, and it is about that H1 disk is about a factor of 2 of the optical disk. So these blue points in this plots that you are seeing are actually corresponding to that, actually, right? And what this is showing, and you can infer it straight away by visually looking at this image itself, that H1 extent of these galaxies is nowhere a factor of 2. So perhaps because of the interaction here between the galaxies and also in ramp pressure stripping and other processes, H1 disks have been truncated in this case. That is one thing. But when we estimate what is the where would they lie in DH1 MH1 plot, what we find is that this actually still continues to hold very well for galaxy, despite of the fact that they are going through uh, this interaction here, even though the sizes are much less than the size that we would predict from the optical disk. So this is something which we are now trying to investigate for a much larger sample of galaxies in different kind of environments, different densities of galaxies in an environment, to see to what extent this relation would hold. And then, of course, with deeper surveys, it will be interesting to see that how it changes as a function of redshift as well. So this is now showing you at a much in a more general level that how the dependence of H1 mass of galaxy would depend on the environment. So x-axis here is the stellar mass, and y-axis is the H1 mass divided by the stellar mass of it. And what are these different color points are corresponding to is the size of the uh, dark matter halo. So this is how these have been actually segregated. And on the right hand slot, what has been done is that in addition to segregating these on the basis of dark matter halo, one has also separated them in different density environment. And what is find that the size of the H1 size of the halo mass actually plays a much more important role than the environment in this, at least in this case. So galaxies which are in much more massive halos, they have much less MH1 by m star, H1 gas mass fraction, right? So this is how, in a generic sense, people are trying to understand how H1 properties of galaxies actually would change with environment and other properties, right? And these are some of the fundamental scaling relations that have emerged out of H1 21 centimeter line observations of galaxies. So what we are seeing here is each of these gray points correspond to a data point from the sample, and these colored points are actually corresponding to the average and the median here in each one of these. So what are we plotting in first panel? It is H1 mass by stellar mass, that is gas fraction, and x-axis is stellar mass. In the second one is actually stellar mass average over the area, that is the gas surface density, and then in third case it is the near UV minus R magnitude of the galaxy. So in each of these cases you find that there is this very nice anti-correlation exists. So what this is showing together is that galaxies which are more massive, which would come here at the top right corner, more bulge dominated, which would again come here at the top, at the bottom right corner of this plot, and also which are red, which will again come here at the bottom right corner of the third panel. So galaxies which are more massive, bulge dominated, and redder, they have got much lesser gas fraction, right? So this is a much more systematic and objective way of stating what I had at a very high level told you in the first lecture in about this Hubble classification, that what we are looking here on the left hand side is the galaxies which are gas poor, and the galaxies on the right hand side which we are looking at are the gas rich, and it also relates to the kind of stars that we form. Now you can also understand very well that what are how to understand this plot of star formation rate and the stellar mass and the main sequence of galaxies, right? So this is so a lot of these observations, because the H1 21 centimeter transition is weak up to this point, have been actually limited to local galaxies. A lot of effort now is now being spent to build more sensitive uh, samples, which will also extend to higher redshifts or go to lower mass of galaxies, or will provide resolved studies of H1 disks of galaxy in the even in the nearby universe. So now, next, what we are going to do is that, so what we have been trying to look at up to this point is that how galaxies are acquiring mass, and once they have gases settled into the disk of the galaxy, the kind of scaling relations that it leads to, right? And once we have these scaling relations in hand, a very interesting thing would be to look at test these in different environments and extend these to higher redshifts, right? So next, what we try to see is that once this H1 atomic gas has come into galaxy, then what happens actually, right? So here, like, there's a wide range of results, a lot of surveys that have taken place. Such studies require multi-wavelength observations. So what we are doing here is that we are going to focus on just a think survey. This is a large program which was carried out with VLA. You can it has a survey website also. You can look at it in detail as you would like. So what it did was I constructed a sample of 34 galaxies carrying sufficient diversity. You can see these are the type of galaxies which the sample consisted of, and then they obtained very high quality data for these galaxies. And one of the things that was done as part of this survey is to look at how within the galaxy itself gas is getting converted into stars, and that's the part we will try to focus. And for that it required not only data that for 21 centimeter line, which traces neutral hydrogen, but also Galax and Spitzer, because these were providing tracers for recent star formation, UV. Spitzer in mid-infrared provided re-radiation from dust. It's uh, corrects for the obscure star formation, because ultraviolet, as we know, will be affected by dust obscuration. Then also this was complemented with data from of carbon monoxide, which is a nice tracer of the molecular gas, right? Because star formation, atomic gas, and molecular gas, all three we need to put together if we want to understand how gas is being converted into stars. Because as we were discussing previously also, that it's the molecular gas which is a direct fuel for star formation, right? So what we are seeing here, so whatever we have talked about till now, we are now looking at it in slightly more detail and trying to put this together, right? That how some of that higher level understanding actually connects to processes that are happening at the kiloparsec or sub-kiloparsec scales in the galaxy. So now in here are this is an example of a one galaxy, NGC 3184 from Think Survey. And you see on the top left panel, this is the neutral hydrogen distribution, right, of the galaxy. And you can see that there is a deficit at the center. But now you see on the second panel, you can see that the molecular gas fills that hole very nicely. So this is describing what we were talking in the morning, that the hole in the center is not because gas is ionized, no, it's because it's actually mostly into molecular. And this is the total H1 plus molecular gas component of the galaxy, right? This is a total sum of it. And this is the star formation rate from uh, 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 Galax and Spitzer observation. So this is the total star formation rate. So you can see that this is now resolved, spatially resolved. So one can actually look at each of these different regions of the galaxy and try to understand how star formation is related. So the question is that we are asking is that how and where galaxy turns gas into stars. So in 1998, Kennicott used a sample of 61 normal and 36 star-burst galaxies, and he came up with this relation called which is known as Kennicott Schmidt relation, and it provides a disk average because these observations did not resolve the galaxy disk. So this was this average star formation law. It found that that the total gas and the star formation surface rate density are related directly proportional to each other, and the slope that turns out to be is like about 1.4. And what is the significance of this plot? Because the slope would be different depending on what are the mechanisms that are leading to the collapse of these gas clouds to the star formation. For example, whether free fall, collision, what all these things would determine what the indices would be. So this is through this we can understand what are the processes that are actually leading to star formation. So what we are so what we want to understand is that two questions. One is that how and where galaxy turns gas into stars, and also in the case of Schmidt law, we want to understand which phase of the ISM is important. Is it atomic or molecular or total gas? Right. So let us first focus on the inner region of the galaxy where we have the optical disk. So we confine to a region where the star formation is taking place and visible in the optical. So this is the overall sample. You can look at this paper, Bigil et al. 2008, if you want to look at it in more detail. So all the maps were put to a common resolution, which is 750 parsec. And then and these are the results that come out of it. So what are we plotting here? Here we are plotting the normalized radius of the galaxy. So R by R25, and y-axis is nothing but the gas surface density for these different galaxies. So what one is finding here that H1 itself, gas surface density itself is varying very little, right? So what is happening is that the local environmental factors are playing a more important role, and H2 mass density also is actually falling off quite rapidly as one moves outside to the outer regions of the galaxy, right? So that's the first quick observation that one get from it. And then let us try to then understand that how this relates to the star formation. So what we are plotting here is on x-axis is the H1 surface density, and on y-axis is the uh, star formation rate density. And then what is plotted here is actually each of these panel corresponds to a different galaxy. So what one is finding that that ISM in this case is dominated by H2 actually, right? And that the Schmidt law actually, what one finds is holds for individual spiral galaxies, and it also holds for the combined distribution, right? So what this implies is that giant molecular clouds, which is actually where the star formation is taking place. If we don't have a resolution, we take this the galaxy as a whole thing. But what this implies that these giant molecular clouds are probably found with the uniform properties, and this gas surface density is only measuring what is called the overall filling factor of such clouds present in the galaxy, right? That's one nice thing that comes out of it. And another thing that comes out of is that the gas surface density actually saturates at something like 9 solar masses per parsec square, and this relation holds for both spiral galaxies and also H1 dominated galaxies. By H1 dominated galaxies, I mean that those galaxies which don't have enough molecular mass. For example, maybe out in this case, we may be talking about the outer regions of the galaxy, or we may be talking about galaxies like dwarf galaxies, right? So, and another thing that has been done is to look for how it is varying with the radius of the galactocentric radius of the galaxy as we move outward in the galaxy. So in the outer disk, where it is actually not molecular dominated, star formation efficiency does not depend only on the gas density, but it also depends on the various local factors also play a role. But overall, as we go out in the outer disk, the star formation efficiency is very low actually, whereas in the center it remains nearly constant. And that's something which, when we were comparing these different galaxies, that also turns out. So this is now a same comparison happening for the dwarf galaxies. These are not molecular gas dominated. Here, what one finds is that the kind of relation between gas surface density one finds with the star formation is similar to what one finds in the spiral galaxies, but in their outer regions. So the environments in the dwarfs and the outer disk probably have the same local factors which can lead to conversion of atomic gas into stars. So this is where actually we have come to, as far as H1 21 centimeter line observations are concerned. That is, we actually have developed a very nice set of scaling relations, right? Where we have a very good idea of how the H1, whether its distribution, the size of the H1 disk is related to the optical disk of the galaxy, or whether how, in what sense actually the total H1 content is related to uh, these different scaling relations here, that in this case, right? And the next step is now to actually relate this to higher redshift objects or galaxies and gas in different environments. So I think we can continue further on this, but I think I would, instead of going further on this, because then things can become faster and more complex, it would be a good idea for us to now actually take a bit of questions, and based on the questions, we go more detail into the things that are of interest as of now, right? Let us proceed that way. So I'm going to take a pause here, and I've stopped sharing my screen, and I want to ask you now to come up with a few questions and then proceed accordingly on the basis of it. We can also go back to topics which were discussed in the morning. Okay, so if there were things which were unclear in the morning, we can actually go back to them as well. But it is important for us to now make connections between different things we discussed in the first lecture and the second lecture. So I will take a couple of minutes break, and I can see that probably you are still uh, trying to gather your thoughts. I'm going to pause for a couple of minutes. So there is a yeah. So there's an interesting question. Someone asked if, whether H1 poor galaxies and H1 rich galaxies uh, uh, form at the same time. So initially, like in the beginning, it's just an H1, right? When the cloud collapses, so it's that's what it starts with. So there is no question of them being H1 poor or H1 rich, but depending on their environment and depending on uh, what the initial conditions are, depending on that, the galaxies may evolve into poor or rich. For example, as I was showing you, let me now again share my screen. So I think this scaling relation, if you go back and if you look at this plot, basically, right? This is telling us like how, or if we rather keep it even simpler, and we look at it like so. So one can see here is that galaxies which are actually present in a group environment, that is in the neighborhood where there are more galaxies, they would actually, due to various processes over a period, are more susceptible to losing their intrinsic gas, right? Whereas galaxies which are more isolated, they would remain gas rich for a longer time, isn't it? So this is something which has been observed, that there exists. So galaxies which are there in the denser environment are gas poor, and galaxies which are there in the gas in less dense environments are gas rich. So, if, for example, if one takes a cluster of galaxy, so in the towards the center of the galaxy, the densities will be much higher, and as one moves outward, actually the density will uh, decrease. So one finds that the galaxies that are closer to the center of the cluster are gas poor, whereas ones that are outside are actually gas rich. And in addition, actually, what one finding is that now, as one is doing more and more observations of such galaxy groups, one finds that most of this transformation actually happens at the group level itself, actually, right? Because you have this hierarchy, right? Galaxies, then they are assembled in groups, and then groups can uh, come together to form clusters of galaxies, right? So at the group level itself, a lot of such transformation takes place. Transformation, whether they becoming gas rich to gas poor, and they merge, and then they go from a more discrete to bulge dominated galaxy. That's the kind of transformation that can take place at the group level itself. So the second question is again related to this figure, is that uh, why is that one galaxy moving so fast that its cloud faces a vicious track while other galaxies uh, appear stationary? So what is happening that these different galaxies, so they are not stationary. You can see that. So one thing that you can see is that for each galaxy below its label, there is a velocity that has been assigned to it. Okay. So, but this velocity, what we are measuring is based on the spectral line. So we know, so we can only measure the line of sight component of the velocity. There is very little we can do to measure the total velocity, right? And in the direction in which it is moving. So only by looking at it, at the fact that H1 from this is actually has been split, we are inferring that in the intergroup medium, this must be moving actually at a very fast velocity, because otherwise there is no other process which can explain, because it is so far away from other galaxies, right? So the only tidal interactions cannot explain this expulsion of gas from it. So it has to be due to ramp pressure stripping, and ramp pressure stripping would happen substantially only when it is moving at a high velocity. Why high velocity? Because this is a very young group. So such groups do not have very dense gas, right? So ramp pressure would depend on rho v square, density and the square of velocity. So if density is small, then it would require very high velocities. So that's the reason we postulate that this actually must be moving at a very high velocity in the intergroup medium. So so don't go by these velocities, right? This is just a line of sight component of it. So, but they may be moving at like a tangential, very fast, like in the plane of sky, right? And that component we are not able to measure. So this is an explanation based on the morphology of the galaxy. So let me also quickly see if there is something which has come up in the chat also, so that we can continue the discussion. Oh, this must be, I may have probably opened the wrong sheet. Yeah. Okay. Somebody saying to ask for PDF and PPTs. When I am present live here, let us first discuss what is there in the slides, and because you would collect 100 slides over the period of this school, and there will be no time to look at them. So what is learned during the coursework is the real useful thing. Yeah, so more questions, so that I know that in which direction to proceed further. why is the scaling really necessary? Can you elaborate a little bit more on it? You can unmute and tell me what is it that you are question cannot unmute. Santosh, members are unable to unmute. Can you allow? You can maybe first raise your hand so that I know who is it, and then maybe I can try and unmute it. Okay. Now try.
Okay. Yeah, hi.
Ah,
Sir, I was curious.
your voice is very faint. Actually, I cannot hear.
Sir, am I audible now?
हाँ अभी
Sir,
अभी
hello.
better है.
Sir, the question is that the HI scaling relation which you have shown in the previous slide. Okay. And my question is that why is the term scaling? I mean, we are scaling what with respect to what? The HI scaling we were talking about. Is it the hydrogen content with respect to the whole baryonic mass of the galaxy, or the or something? I was unable to understand that.
हाँ okay. So let's look at that actually. So these are the plots actually, right? So let us look at the one related to scaling relation. This is the one, right? So what is plotting here is the gas fraction on y-axis. So total H1 mass divided by the stellar mass of the galaxy, right? And on in the left panel, x-axis is stellar mass. This is surface density, and then this is the near UV minus R color. So near UV minus R color will be actually sensitive to star formation, right? If a blue galaxy, right, would appear here on this side, on the left hand side of the plot, and on the right hand side, you will have the galaxy which is redder. So redder galaxy, if we go back to our this plot, you can see that it will correspond to these kind of galaxies, right? And bluer galaxies are here. So this is what this plot is representing. And this is on the extreme left we are looking at is the gas fraction. So gas, as the galaxies are getting gas poor. So on the right, bottom right, you have galaxies which are very gas poor. Okay, so again, like here, you can relate to this classification. So what one has is from these measurements is a scaling relation that is telling us that the galaxies which are more massive, more bulge dominated or redder, they have actually uh, less gas fraction, right? So the advantage of being able to make a measurement like this and quantify it, that then it can actually be examined, right, across for example, we can ask the simple questions like, let's say, if I take galaxies now in different environments, if I take galaxies which are isolated and I make another sample of galaxies which are in which they are in group. Now in these two cases, would they come and follow the same scaling relation or not? And depending on whether they do or not, I will know uh, that which physical process is actually important in different environments. So that's why scaling relations become important here, because they bring out a certain aspect. They relate to observational properties of the galaxy, and then by comparing them based on different control samples, for example, we can understand what is it that driving this kind of scaling relation and how it will change in different environments, right? Because otherwise, if I don't have an actual measurement, then I cannot. I can just know that, okay, something very broad like this happens, but then how it, actually I cannot really go more detailed or deeper than that, right? But this is why having actual measurements helps. So there is something more on chat. Something asking what is Okay, good. So you understand. I'm trying to. Okay, so this was your question only, and let me look at if there is something on. What do you mean by dust in galaxies? So right, so we have these different phases in ISM, right? So for example, gas phase is the most prominent phase that we talk about, where the hydrogen, helium, and all the metals are in gas phase. But in certain conditions, they can actually condense into form dusts, right? And this usually, these are basically solid particles, actually, of the size of the order of, let us say, uh, microns, actually. And then what happens that they would actually, in that case, uh, typically block ultraviolet light. And as you go to longer wavelengths, because those wavelengths get longer than the size of the dust grain, they are no longer effectively blocking. So if you recall, if I go back to, for example, the plot which I showed in the morning, which was related to the discovery of the ISN, right? So let me share again. Right, so this is what it is, right? So there's a molecular cloud here, and it has got dust particles in it. And you can see that as we go to longer wavelengths, as we go more than a few microns, then actually uh, the stars which were hidden behind this molecular cloud, which had dust, actually are become visible, right? So this shows that there is a presence of this uh, molecular cloud, which has got molecules and dust particles in it. Dust particles in it are causing the scattering or extinction of the ultraviolet photons. That's why this is a dark patch here. Yes, Mr. Subrata, please unmute.
Yeah, can you hear me?
Yes, clearly.
Yeah, in that H1 scaling relation, this is just a small clarification. There were two colors, I mean, circles of two colors, blue and red. So, what if you can go back to that slide, H1 scaling?
Yes, yes. So one is, it's very simple. One is corresponding to median of the
Oh, okay,
samples in
okay.
that one. Another is corresponding to the average.
Average. Okay, okay. You had told that. Yes, yes.
Yes.
Okay, okay.
So yeah. So one is median and one is average.
One is average. Okay.
Yeah. Simple average.
All and they are more or less overlapping. So
Yeah, they are more or less overlapping. Yes.
okay, thank you. Yeah. So I was saying that you said that relationship between velocity and density, uh, or did I catch it correctly? Like some product should be a constant. So if the
Not
uh,
constant RAM pressure stripping, actually.
so can you please
That
restate that? I did not
so
catch that.
so density into the square of velocity.
Acha, okay.
So if the density is small, then it has to move at a very high velocity for a force to be effective. That's what the inference was.
Okay, thank you.
Hmm. So a lot of what we have discussed today, as you can see, is related to a lot of atomic physics, actually. And so most of it we also read about in our master's level atomic physics also, especially H1 21 centimeter line. So someone has asked if we are able to take different regions of a single galaxy and determine star formation rate for each of them, how can we know about the evolution morphology of what particular type of galaxy? I mean, will we be able to classify them as AGN, starburst, normal galaxies, and determine the shape? So, so there are a lot of questions in it. So, if you want to classify a galaxy as an AGN, then uh, you have to straight away ask the question, what is an AGN? So then AGN is basically an accreting black hole. So you will have to look at its nuclear region. So if you obtain an optical spectrum of it, for example, you will see various emission lines that are characteristic of nuclear, AGN. So you will see lines which are very broad, for example, that would give, you will notice, and you will find that the line ratios and the underlying continuum of the spectrum will be very different from what that you can obtain from, let's say, stars, because stars generally black body, and AGN would be a power law which will be emitting over such a broad wavelength. So that's what you will have to do. You will not, by looking at star formation rate in different parts of the galaxy, you cannot really say whether it's an AGN or not, right? So, and then talking about like whether it's a starburst, yes, that's a nice thing. If you can measure star formation rate of a galaxy as a whole, then you can determine whether it's a starburst or just a normal star forming galaxy or not, because star formation rate is what you need to measure. So for that, you can make an observation of that galaxy in, for example, H alpha, which will give you a good way of star formation rate. You will have to correct it for extinction, but nevertheless, there are well-defined prescriptions to do that, for example. So yes, so depending on, and if you want to measure the shape of the shape of the galaxy will actually depend on, again, what shape of what that you are talking about. If you are talking about the shape of the optical disk, then you have to make an optical observation. If you want shape of the H1 disk, which extends much further, then you have to make H1 21 centimeter line observation of it. If you are interested in like where the old and young stars are distributed, that kind of a thing, then you will have to make an observation in UV, optical, and infrared, all three, and that would allow you to get an idea of shape and the distribution of stars. So yeah, so to answer this question would require different types of observation of galaxies. So if there are more questions, you can unmute and ask. Actually, that is.
Uh, Hello, may I ask one more question?
Bilkul.
Yeah.
Yes, please.
Actually, I had asked this question in the morning, but perhaps when you answered it, I had to attend to something else, so I
Okay.
could not catch that answer. So I had asked about this question of, in the morning session you had said some like what percentage of a galaxy will be atomic hydrogen, how much will be molecular, and how much will be in the ionized plasma state. Some percentage
Ha.
distribution.
So that
So,
was, yeah, that was not for any galaxy.
no, that
That was for Milky Way,
Milky
our
Way,
own
yeah,
galaxy.
yeah, Milky Way. No, my question, it's slightly broader, more general question is, do we have a similar thing for other galaxies also? Like, how do we measure the total mass of a galaxy, and then how do we find out the H1 mass and molecular mass and all that? So, is there
Oh
some
yes,
general?
yes, especially in the nearby universe, it is possible to carry out, for example, H1 21 centimeter line observations will provide H1 mass of the galaxy. Then,
Right.
if we provide do CO observations, we will get the total CO content, molecular gas content of the galaxy from that, using some scaling relation. And then using H alpha, we can get an handle on what is the ionized gas component in the galaxy. So using these, we can actually get an idea of what So these proportions would vary from galaxy to galaxy, actually,
Galaxy.
in the sense like of what galaxy type it is.
Okay.
Right. For example, if you go to early type galaxies, then they would have very little atomic and molecular mass, right?
Okay. Mhm.
Hmm.
So what was that ratio for Milky Way? If you can just repeat, just for knowledge and in general knowledge.
हाँ बिल्कुल, that is if it is by mass, then it is 60% atomic,
Okay.
then approximately 25% is ionized, and 15% is molecular,
Molecular.
and that
Okay.
is by mass actually.
Okay.
And yes, the volume filling factors can be different, of course.
Mhm.
So this is by mass actually.
Okay. Thank you.
Shlok, yes, please.
Sir, what about other molecules present in the galaxy? Like apart from CO observations, do we do any other spectroscopic technique for measuring some other elements?
Oh yes, actually. So there are different techniques through which more than what you call maybe close to 100 actually molecular species have been detected in dense molecular clouds in our galaxy and also in some external galaxies. CO is just a very uh, convenient indicator to detect molecular gas as a whole. Other tracers are weaker and they also are produced in more rare conditions. So they are not something which can be used, for generic surveys or observations. But yes, there are a lot of other molecules like formaldehyde, SU plus, OH, and various other things that have been detected in our own galaxy and external galaxies also.
I think we should explore.
Thank you.
Hello, sir. Am I audible?
Yes.
Sir, in morning you said that those atoms or those particles used to stay in the excited state for almost 10 raised to 7 years. Sir, like we have learned from undergraduate physics that particles cannot remain for long time in excited state. So, sir, how is that possible? Like, is there any mechanism or something like that?
Yeah. So see, that is what you learned is from atomic physics, and what I said is also based on atomic physics. And it will just depend on what transition that you're considering. The kind of transitions that you have come across probably most of the time are dipole transitions, right? And for the dipole transitions, generally the Einstein's A coefficient is uh, pretty very large, which means that the transition probability from excited state to ground state is very high. So, for example, 2p to 1s, right? It is 10 to the power 9 per second. That's the Einstein's A coefficient. Whereas if we look at 21 centimeter line, it's a magnetic dipole transition. That's the reason that its Einstein A coefficient or the transition probability is extremely small, and a result of it, it will remain in the excited state for a long time. So this is coming from fundamental physics actually, and this is the way to understand it.
Thank you, sir.
Yes, I cannot hear you actually. If you also raise your hand, then your name would come on top. That way I will also know. Okay. Uh, is it Dr. Subhash Kumar? I am unable to hear you right now.
Sorry, it was by mistake that hand went up.
Oh, no problem. So one of the interesting things that if as one of as if you want to know more about H1 21 centimeter or radio observations, because this is 21 centimeter line happens at radio wavelengths, then you may want to look at details of projects like Square Kilometer Array, for example, or Giant Microwave Radio Telescope, which is currently a very sensitive telescope in India. And there are several new, more sensitive telescopes coming up in Australia, for example, Australian Square Kilometer Array Pathfinder, then MECAT telescope in South Africa, very large array BLA in America. So these are all new telescopes which are carrying out very nice, very deep observations of neutral hydrogen in our galaxies. So within a few years, we will have many more new results coming out from observations from these telescopes, and it will be of your interest to maybe just Google and see what kind of different projects that are going on there. And often they have websites where they actually put out nice results that are coming out from the telescope. So all this can be very interesting and exciting for you to just look at. And if you are on social media, you can also follow these projects and or telescopes using either Twitter or Facebook. That way, you won't have to search. Whenever something exciting happens, you will get an update. That's another way to keep in touch with these activities. And often, when a nice result comes out, a paper is published, and even their websites, there are articles written which are not very technical to start with, but they provide reference to the original discovery article also, so you can uh, and read that general article first to get an idea what is going on, and then go to the actual research paper and then try to understand that as well. So let me know if there are more questions. In a couple of minutes, we are going to close. Otherwise, if there is, I can also suggest if there are some topics of interest in your mind right now, I can also suggest different resources or books also. If that is one thing that anyone would like to know. If you can be specific about what topics actually, because then there are 4 general books on astrophysics and astronomy that you must be aware of already. But I was thinking more specific if related to something that we have talked about today. If that is what. So H1 21 centimeter line, since it's so you can look for different radio astronomy books. For example, radio astronomy is a book by Rolf. It's a nice textbook which also explains radio astronomy, and it also has very nice description of H1 21 centimeter line observations and its basic physics. You can look at it. Then there is a book on interstellar medium, which is by Draine. The title is The Physics of Interstellar Medium. So that book covers all different phases of interstellar medium, their associated physics, atomic physics, and it also has several chapters on H1 21 centimeter line also. So and that is from an astronomy perspective. So you can look at that. Then there are books on atomic physics. For example, you can look at Theoretical Astrophysics by Padmanabhan, for example. I think it's volume 1 will give you a nice derivation of H1 21 centimeter line transition probability and other things from quantum based on quantum mechanics. You can look at that and what are the different physical processes give rise to line width. All that you can find in theoretical astrophysics book, and there are lots of other atomic physics books also. But straight away, these are the 3-4 books that come to my mind for H1 21 centimeter line. Okay, so since there's no more questions, I think let's wrap up now. It was really nice discussing with you all, and best wishes for your various projects.